If you have gone to the doctor at some point, you might have contributed to a large dataset that is used for disease study like this. Each number in the table represents how likely one with the labeled biological sex and age group would get the disease of our interest. Of course, these could also be tables of any other measures of the disease. Now, what if I want to know how likely I would get this disease regardless of my age, just as a female? And there are many questions similar to this that we could ask. These overall probabilities that depend only on one variable are called the marginal probabilities, which are just as important as the original data table we had. Now, the more general question becomes, how do we calculate these marginal probabilities fast? Let us first think about what is the most trivial way to calculate marginal probabilities. Consider a simple model with 3 binary variables, meaning they each takes a value of either 1 or 0, and 2 known joint probability functions as shown in these tables. Notice that these are likelihood, which are basically just not normalized probabilities, and we will leave the normalization to the very end. Like we said earlier, we want to calculate marginal probabilities, which are probabilities that depend on only one variable. The most straightforward way to calculate these is using the exhaustive listing and addition method. We will simply write out all the possible outcomes, count their corresponding likelihood, then add them up. Here is a table with likelihood of all outcomes of these 3 nodes. These are calculated by the products of the 2 joint probability functions. For example, the first row comes from the product of likelihood of when x1 and x2 are both 0 from the top table, and when x2 and x3 are both 0 from the bottom. I have also added all the likelihood numbers together, which is 42, and this number will be used as our normalization factor. Now we can proceed to the last step, which is simply adding the likelihood for all the rows with x1 equals 0 and all rows with x1 is 1. Then divide by the normalization factor 42, we get the marginal probability for x1. Similarly, we can find the marginals for all 3 variables. So, this doesn't look so bad, right? In fact, the number of steps in the calculation we just did is in the order of 2 to the third. Or more generally, for a system with n nodes, each with s possible states, this method of calculation is in the order of s to the n, meaning that as the system gets larger, this problem gets exponentially more computationally heavy and time demanding. Now things are looking not so good. Are we stuck here? Fortunately, there are always people out there doing fantastic work to solve these problems. In 1982, Israeli-American computer scientist and philosopher Yehuda Perl came up with this brilliant idea called belief propagation, or the sum product algorithm, which can be used to find the marginals through information propagation in a network. You might wonder, sum product sounds just like what we did, but in reversed order. How does this help? Well, the key here is that the calculations are done in a network with several additions or multiplications happening simultaneously. In fact, the computational cost for belief propagation is only in the order of s squared. This method improves the computational cost of the problem so significantly that even for a system that is just slightly larger than what we have here, we could confidently throw the exhaustive addition method out of the window. Going back to the simple example we used earlier, to do a belief propagation, we first rename the joint probability function piece as factorization functions f. Then we reorganize the system as a factor graph, in which we distinguish variable nodes in blue circles and factorization functions in yellow squares. Edges in this graph connects the factorization function with its variables. Lastly, we write the factorization into vector form, which would help simplify our calculations later. Now we're ready for the propagations. The main idea of belief propagation is passing messages back and forth between the variable and factor nodes. Each message is a guess of the marginals of a node based on what information it has gathered from other nodes. Propagation 1 always starts from passing a guess message from variable to factors. Since there's no previous information gathered, all messages in propagation 1 from the variable node are 1, 1, meaning it's equal probable to be in state 0 and state 1. Once the factor node receives messages from the variables, they will combine the information they received into a new message and send them back to the variables. Consider the messages from factor b to variable 3. The first step is to process messages from all the other nodes. The messages received is then multiplied with corresponding rows in the factorization. For example, the first one in message m corresponds to when x2 is 0, and thus it is multiplied when all rows in fb with x2 0. If there are multiple m's in this stage, they are all multiplied together in the similar manner. Once we have message processed with fb, it is summed over all the other variables except for x3, so that it becomes a 2-entry message, where first entry corresponds to the probability of x3 being in state 0. This message that fb passes to x3 tells x3 what other variables think its marginals are. In this case, is 1, 2 before normalization. After calculating all messages from factors to variables, we obtain propagation 2 here. The outgoing message from variable to factors for the next propagation is the product of the received messages. For example, the outgoing message from x2 to fb in the next propagation will be the product of all messages that x2 has received except for the one from fb itself. In this case, the only other message is from fa, so x2 simply passes message from fa to fb without processing it, and vice versa. To show how to combine factor to variable messages, we consider this side example, and this is unrelated to our primary example. Now x2 used messages from both fa and fc to create the outgoing message to fb. The two messages are multiplied in an entry-by-entry manner and then simplified. Now going back to our original example, follow the node to factor message passing rule, we get propagation 3. If the variable node is only connected to one factor node, this message it passes to the factor is always 1, 1, as shown in orange here. We then keep passing messages between the factor and variables until the messages pass reaches a stable state. The left figure shows messages from the previous propagation. It is compared with the propagation on the right side. Propagation 3 and 5, which are both variable to factor passing, are the same here, meaning that the system has already reached a steady state. We will go one step further to confirm that factor to variable also reaches stable state, which is propagation 4 and 6 here. Once we have the stable state, we can then calculate the marginals by combining messages of the factor to variable node propagation. The way to combine these messages is the same as before, and at the very end, we will do the normalization as promised. Now, let us compare our results to the exact marginals calculated earlier. Comparing with the result from the exhaustive addition method, we see that belief propagation gives the correct marginals, while the order of calculation is only the number of possible states squared. As the plot shows, the belief propagation method does have significant advantages as the number of nodes increases, while preserving the accuracy of the result. If you enjoyed watching this video, please leave a like or comment below. Thanks for watching.